Right, we are still with Avery St. Dizier, and you can continue your talk to finish off with the next topics.
All right, so now I'm going to tell the story of where that partial log concavity of Littlewood-Richardson coefficients came from and how we kind of arrived at it. So the story actually starts with taking a polytopal perspective on polynomials via their Newton polytope. So the two ways to think about polynomials are as these continuous functions, but you can also think of them as discrete objects. And the way you do that is by taking the Newton polytope, which is just the convex hull of all the exponent vectors that actually appeared in the polynomial with a non-zero coefficient. So here are two polynomials that have the same Newton polytope. And for this one in blue, I marked the points that actually appear and just take the convex hull of those and you get their Newton polytope. So as this example already shows, the Newton polytope can contain some other stuff as well. And also different polynomials can have the same Newton polytope. And in this talk, I'm going to generally think of the points of the Newton polytope as being labeled by the coefficients that appear. So it's more of a geometric way to think of a polynomial. So one of the questions we started with was, can we describe the Newton polytopes for various things in algebraic combinatorics? So I've told you about Schur polynomials now. So what's the Newton polytope of the Schur polynomial? Here's two examples. We know the Schur polynomial is a symmetric polynomial, so their polytope should be highly symmetric. And this actually is quite old. The answer was due to Rado in the 1950s. The Newton polytope of the Schur polynomial is called the Permedihedron of the partition you started with. You take your partition lambda, permute it in all possible ways, and take the convex hull of those. It's a really nice, well-studied polytope. The edge structure of the polytope corresponds to the weak Brouhat order on the permutations, with the edges being the adjacent transpositions. So we know what the Newton polytope of the Schur polynomial is. Now I can draw this picture. So I have my partition being 4, 2, 0. I take its Newton polytope, and I mark all the points with the coefficient of the Schur polynomial. And we stared at these for a while and thought, what interesting questions can we ask? And the first question that jumped out of us was, where are the zeros? We couldn't see any, and a priori, there's no reason they couldn't be there. And around the same time, Monakel, Tokjun, and Yang actually gave a name to this property. They said a polynomial f has saturated Newton polytope, abbreviated SNP, if every integer point actually came from something in the polynomial having non-zero coefficient. So no zeros in the picture. And they found SNP throughout algebraic combinatorics among lots of symmetric functions, including the Schur polynomials, the skew Schur polynomials, Stanley symmetric functions, and certain generic evaluations of symmetric Macdonald polynomials. So very prevalent. And they conjectured it for quite a few other polynomials outside of symmetric functions that I'll talk about in a bit. So there's one question answered. But the other natural question, even from the simple picture, is how are the coefficients distributed? We see this nice clear pattern here of the big 3 in the middle, smaller things around it, 1's on the boundary. And the idea for how we chose to look at this was to, instead of thinking about this geometric data spread out in space, focus in on lines in the Newton polytope. So we're thinking about sequences instead. And for the Permedihedron, the natural lines to think about are the lines in the usual root directions, because that's the integer lattice of this polytope. Now, there are two properties of sequences that come up. Unimodal means that your sequence goes up for a while and then goes down for a while as you read along the line. And the stronger property is the discrete log concavity. Anything in the sequence squared is at least as big as the product of its neighbors. And it is actually stronger. If you're positive and log concave, you also have to be unimodal. So the question we came to, based on some computational evidence, was, do the Schur polynomial coefficients form unimodal sequences? And possibly even log concave sequences.
Can I ask a question?
Yeah.
I mean, these are the dimensions of weight spaces, right, for GLN irreducibles. Is that right? Or,
It is.
so then your root directions, those are SL2 representations. So wouldn't they have to be unimodal?
Yep, and I'm about to say that as well.
Oh, I see. Okay.
Yeah, so that was going to be the next thing, is why you might think this from representation theory is from the crystal operators. So to give a quick introduction to those, there are these maps Fi on semi-standard Young tableau that try to turn an I into an I+1 in kind of the most efficient way. And the way you do it is you pretend all your i's are closed parentheses, all your I+1s are open, and you read your parentheses up columns, left to right, and then remove any matched pairs. So when you do this in this example, you read open, close, 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 open. Remove your matched pairs, and you're left with just these three on the end. And now turn your rightmost close into an open, which is like turning an I into an I+1 to get something like this. And these actually come from representation theory, where you can use them to do various things. In general, you have this graph called the crystal graph, where you put down all of your combinatorial objects and all of the crystal operators between them. And in representation theory, you can use this to show that you can use this to compute, for instance, Littlewood-Richardson coefficients. You can use this to compute irreducible decompositions of tensor products of representations. And the way you do that is essentially count how many connected components in the tensor product of the graphs are isomorphic to the crystal graph of the representation you care about. And now the reason this implies unimodality is by looking at orbits. So I'm going to go back to this picture and look at a particular line here. I guess all the lines are the same in this picture, but what you can do is imagine all your Young tableau, which are counting weight multiplicities in your representation, and sort them all according to orbits under F1, which turns i's into I+1, which should be the direction of this line. And now when you look at all your orbits and think about how F1 works, at the far end of each orbit, your parenthesis word should be all closed, and at the other far end, they should be all open. So what you notice is that immediately implies you have to have symmetric, your orbits be symmetric around the midpoint of this line. So you have to see unimodality along any of these lines. So that's one place unimodality can come from. Is that what you were talking about with your question?
Well, I didn't think it really needed any crystal structure. I mean, if you have an SL2 representation, then the weight space for 0, then it's a sum of irreducibles. And the way the irreducibles stack, the value at 0 has to be bigger than everything else, and it's unimodal away from 0. So the dimension of the one weight space is the same as the -1.
Oh, okay.
I guess it has to be either all even or all odd. So maybe I have to take that back, but if you mix 0 and 1 eigenspaces, then you could potentially not have unimodal, but you're definitely restricted. It might be nice to say you're restricting and you're getting an SL2 representation, and then I think they have to have the same parity. So unimodality would just follow from that without appeal to crystal structure. I don't know. Maybe I'm not understanding.
Yeah, so I wasn't aware of that, so thank you. So this is the thing we knew how to do at the time, was to use crystals, which were very combinatorial, and we were all combinatorialists looking at it. So we were missing some of the representation theoretic background that would have helped. And when you use crystals, you get unimodality along any of these lines, EI minus EI+1. but we suspected there was more unimodality as well for any root direction, not necessarily one of the adjacent root directions. So we made this question. So is it true that the Koska numbers are log concave in any root direction? Just optimistically based off some data and this partial unimodality. Now at this point, I owe an explanation because I started off talking about Littlewood-Richardson coefficients, and now I'm talking about Koska numbers, so how do we get between them? And that's where this weird condition about the skew shapes having at most one box in each column comes from. It turns out this condition is exactly what you need to kind of embed the Koska numbers into the Littlewood-Richardson numbers. When you have this condition, if you take the difference of nu and mu and use that as your alpha, you get that k lambda alpha is the Littlewood-Richardson coefficient. And you can reverse this map. If I just hand you lambda and alpha, you can write that as a Littlewood-Richardson coefficient by taking partial sums to form your two partitions, as indicated in this picture. You use the full partial sums to make your nu and ignore the top row and use the partial sums to make your mu. So when we look at these partitions, we're secretly just looking at Koska numbers. And in particular, when we translate the log concavity for Koska numbers that we've been looking at, we exactly get out these weird difference of fundamental weights. So that's where this special case of a Kuhn-Kauf conjecture comes from. So it's enough to prove just the log concavity of the Koska numbers, which looks a little more natural with differences of, or with the roots instead of the differences of fundamental weights. So now to get into some of the machinery behind this, it's called Lorentzian polynomials. So first I have to introduce a definition that kind of bundles two things that I've talked about so far, which is called M-convexity. And here's the technical definition. A set of integer vectors is M-convex if when you pick any two guys in your set and an index I where alpha is bigger than beta, then you can find some other index j where alpha is smaller than beta, and so that if you step inward from each of those points along the root direction ei minus ej, you stay inside the set. So here's the picture. Alpha is bigger in I, beta is bigger in j, beta is smaller in I. I can find a j so that I can step inward from both and stay in the set. The M stands for matroid, and if your set is the indicator vectors of the bases of a matroid, this is just the symmetric basis exchange. And there's a nice polytopal way to think of this, and it's that the support of a polynomial will be M-convex if and only if you have the saturated Newton polytope, and your Newton polytope is roughly a permedihedron, but not quite. You have to go slightly out and get what's called a generalized permedihedron. So a generalized permedihedron is a regular permedihedron, but you're allowed to take your vertices and move them around in any way you like that doesn't change the direction of the edges, other than possibly getting rid of an edge and making it 0. So in this picture, I took these two vectors, these two vertices, and I moved them along their edges till they became the same vertex. These two I just moved out a little bit till they became a little smaller. So M-convexity bundles the saturated Newton polytope property and the Newton polytope being a generalized permedihedra. So now I can define Florencian polynomials. This is due to Brändén and Huh in 2019. A homogeneous polynomial of degree d with non-negative coefficients is Lorentzian if two things. You have to have M-convex support, and this other condition is a condition on the derivatives. When you derive your polynomial down to a quadratic any way that you like, view that quadratic as a quadratic form. It'll have at most one positive eigenvalue. So I'll give an example of why this condition, even though it looks kind of weird, is actually very nice in a second. I just wanted to mention that Lorentzian polynomials come from two simultaneous generalizations. They generalize the volume polynomials of projective varieties in algebraic geometry and the stable polynomials in optimization theory, polynomials that have no zeros on the open upper complex half space. So here's a quick example to make sense of that definition. here's two polynomials. They are both homogeneous. They have positive coefficients. The Newton polytopes are both the line segment from 0, 2 to 2, 0. So they're generalized permedihedra and they have S and P. So there's M convexity. And when you write down the matrices, their quadratic forms, you put the coefficients of the square terms on the diagonal, half the coefficients of the non-square terms. Here you have eigenvalues that are both positive. So that's not a Lorentzian polynomial. And if I just tweak this and make the square terms have half the coefficient they had before, now I have only one positive eigenvalue. So that is Lorentzian. So why do we need this? Well, to quote Brändén and Huh, Lorentzian polynomials bridge continuous and discrete log concavity. So here's the relation to discrete log concavity. You use what's called this normalization operator, which takes a monomial to it's scaled by the product of the factorials of all of its exponents. Think of this as priming your polynomial to be derived a bunch of times and not have the coefficients explode. Now, if you take any polynomial that's non-zero, such that its normalization is Lorentzian, you get exactly discrete log concavity of its coefficients along the root directions. So this is the discrete log concavity following from the Lorentzian property. And here's a short sketch of the proof just to see how that spectral condition really comes in. And the way it works is, let's just say we're dealing with x1 and x2. Take a bunch of partial derivatives of your polynomial, roughly in the direction alpha minus e1 minus e2, set everything else to 0, and assume you're going to get a Lorentzian polynomial out of this. The polynomial you end up with exactly uses those three coefficients that are adjacent to alpha in that root direction. And when you write down their quadratic forms matrix, you get this. And if this thing is Lorentzian, it should have at most one positive eigenvalue. So its determinant has to be non-positive, which is exactly where these root direction log concavity inequalities come from. So somehow the spectral condition magically lets discrete log concavity fall out. Now for continuous log concavity, you get the same story. If your polynomial is non-zero and has normalized, its normalization being Lorentzian, then the function itself, the normalization is itself continuously log concave. Its log is a concave function on the positive reals. And even more is actually true. The Lorentzian property itself is equivalent to two stronger versions of log concavity. Strongly log concave, meaning that products of derivatives of your polynomial are log concave, and completely log concave, meaning products of sums of partial derivatives of your function are log concave. So the Lorentzian property is very strongly related to log concavity. So to finish out the ideas from earlier, I need to show something is Lorentzian. And what we were eventually able to figure out is that the following thing is Lorentzian. Start with any permutation, take its Schubert polynomial, invert all your variables, multiply by this long monomial of all the variables to the n-1, and normalize that mess. That thing will be Lorentzian. And the choice to do this comes up geometrically by thinking about matrix Schubert varieties. The Schubert polynomials are what's called the multi-degree of them, and when you untangle definitions, you can show that this expression is their volume polynomial. So that's where these come from. Now, to actually use this, something really cool happens when you restrict to Schur polynomials. When instead of a Schubert polynomial, you use a Schur polynomial, the symmetry essentially tells you that when you do this process, you get out basically just another Schur polynomial. And all you do is take the complement in a rectangle to do this. You can see this from the representation theory, if you like, or if you know Gelfand-Settlin polytopes, you can see this operation directly as a map, affine map on the Gelfand-Settlin polytope. So now to use this, as a consequence, the normalized Schur polynomial is Lorentzian. And then immediately from that, because of the general theory of Lorentzian polynomials, we get the discrete log concavity of the Koska numbers and the unexpected result that the normalized Schur polynomials are also log concave. Now, to close out the story, we had to pass the Schubert polynomials for some reason to prove something about Schur polynomials. So it would be nice if we could finish the story for Schubert polynomials as well. And some of the story we already knew going in. We knew that Schubert polynomials had saturated Newton polytopes and that their Newton polytopes were generalized Permedihedra, because prior study of this had given a way to decompose their Newton polytopes into matroid polytopes in a nice way. So that told us M convexity held for Schubert polynomials. And additionally, because of the way this operation of inverting your variables and multiplying by a monomial looks on Newton polytopes, what happens is the Newton polytope of your Schubert polynomial, when you flip the variables, you're just reflecting across all your coordinate axes, and multiplying by this monomial is just shifting your polytope back to the positive orthant. So at no point did you actually change how your coefficients were sitting in relation to each other inside the polytope. So just from the fact that this thing is Lorentzian, you immediately get the discrete log concavity of the coefficients of the Schubert polynomial as well. And it'd be really cool to see a combinatorial proof of this. I have no idea what such a thing would look like. Same for the Koska numbers. But unfortunately, not all is well. It turns out, even if the normalization of a polynomial is Lorentzian, this operation of inverting your variables and multiplying doesn't have to be Lorentzian. So we ended up leaving this as a conjecture. The consequences of discrete log concavity are still true, but we didn't know how to prove the normalized Schubert was Lorentzian. There are a few interesting special cases we can prove. These two pattern avoidance conditions correspond to demanding that all of your coefficients be as small as possible. So for this top one, this is equivalent to being 0, 1. In that case, your normalization is Lorentzian. Or if independently you demand that each coefficient of your Schubert polynomial be as big as possible, that's equivalent to avoiding these two patterns. In that case, we know your normalization is also Lorentzian. So the question I wanted to finish on was, what else is Lorentzian? Is there anything special about just the Schubert polynomials? And this comes back to the saturated Newton polytope property of Monaco, Tokchun, and Yang. Aside from all the symmetric functions they proved that it holds for, they also conjectured it holds for a bunch of other things, including Schubert polynomials, double Schubert polynomials, Grothendieck polynomials, which are inhomogeneous versions of Schubert polynomials, and key polynomials, the characters of the Dizier modules of the general linear group. All polynomials from algebraic combinatorics, none of which are really symmetric polynomials anymore. And it turns out we think much more is actually true. We think all of those same polynomials also have the Lorentzian property, so the discrete log concavity and the continuous log concavity. And we add one more to that list, which is don't just restrict yourself to finite dimensional representations of GLN, but allow infinite dimensional representations as well, and then do some things to truncate your characters and have that make sense with the Lorentzian property. And that's it. Thanks.
Let's all thank Avery for the wonderful talk.